Alright, I'm going to take a little bit of a break here. Instead of going to example 3 here, I'm going to switch. Hopefully you have this handout from class, and I'm going to take a look at the first two, question 20 and question 21. So if I just take a look at that right here, we've got these two questions, 20 and 21. They're quite related. They're sort of, if you'll notice, in 21 it says if the car in problem 20 had, so they go together. So reading the first question, 20, it says a movie scene has a car fall off a cliff. If the car took 5.5 seconds to reach the ground, how high was the cliff? Okay, so well, let's try drawing this. So here is the cliff. There's the ground, and then we have a car. Let's see the car. There, something like this. So it's moving this direction. Now the path of the car as it falls is going to be the right hand side of a parabola, kind of going like this. Boom, it hits. This will be sort of like the beginning of the interval of time that we're interested in, and this will be the end of the interval of time that we're interested in. And the question is, how high was the cliff? So in this part here, how high was the cliff? So in kinematic terms, I guess what they're asking here is, what was the change in displacement? If they started here and they ended there, what was the change in position, but specifically the change in the y position, right? So in other words, if they started here and ended there, this part here will be your delta dy. Okay, your delta dx, this one over here, this would also be the same as this part here. That would be your delta dx. That's how far away from the cliff that the car landed. So that's actually the question for the second part, is the delta dx. Okay, well, in solving this question, and maybe I'll erase some of this stuff just so that we can see it better. In solving this question, we're going to do what we normally do, is we're going to separate the motion into the x and the y components. So we'll have maybe the x here and then the y over here. And now let's fill in everything that we know. Okay, so first of all, it says it took the car 5.5 seconds to reach the ground. So really, the delta t part, the time here, it belongs on both sides. That's the only thing that's on both sides. This is 5.5 seconds here, and delta t equals 5.5 seconds here. So while it was moving horizontally, it traveled for 5 seconds, and while it was moving vertically, it moved for 5 seconds. A reminder that for our horizontal motion, the only thing that we're going to be using is v is equal to delta d over delta t, and this will be vx. It's how quickly it's moving horizontally, and this would be how far it moved horizontally. So along the way, it's going to start with some vx. Alright, and that Vx will be constant the whole time. So the whole time it's going that same horizontal velocity. So that is a constant velocity. Delta dx will be, as I said before, this distance over here. That would be our delta dx. So horizontally, these are my only two things that I'm interested in here, Vx and then delta dx. Vertically, the vertical motion, there is acceleration. There's constant acceleration. So then really I'm in a situation where I'm going to be using my big 5. So thinking about our big 5, we've got acceleration, and acceleration in the y direction, which is downwards. I'm going to be accelerating negative 9.8 meters per second squared. So unless it says that it's not on Earth or something, you can go for that 9.8 meters per second squared. Now, when the car is traveling horizontally and it goes off the cliff, the initial vertical velocity is going to be 0. So to begin with up here, it's going to be 0. Vy1 is equal to 0 meters per second. You're going to find that's true whenever you have something that is shot horizontally or is moving horizontally. It's not moving vertically. So initially this 1 is, saying over here, right? And then the y means vertically the velocity. So at the beginning period of time, its vertical velocity is 0. At the end, I don't know. Vy2 So at the end, so at the beginning it's not moving very much at all. By the end it's moving vertically quite a bit. So I don't know that one. What's left is my delta dy. And that's really what I want to find out, right? So the way our big 5 works, I'm going to say, at least initially, I'm going to pick the one that doesn't have Vy2. All right, so we can figure this out. I can say the one that does not have V2 in it is equation number 1, so which is delta D is equal to V1 delta T plus 1/2 A delta T squared. Since I'm talking the vertical, though, I'm going to say delta dy is equal to Vy1 and then Ay, because I'm talking about our vertical motion. So now I'm all right. Okay, well, if my Vy1 is 0, that means that this term is 0, and I'm going to get plus 1/2 times negative 9.8 multiplied by 5.55 all squared. So here I'll get negative 4.9 times 5.55 squared. So using my calculator here, I'm typing out 0.49 times 5.55 squared equals, and I get, and it'll be a negative number here, negative 15.09 meters. Okay, so my answer to the first question here is, how high was the cliff? Well, if the change in vertical position was downwards, that means that the cliff must have been 15.09 meters. And I'm not going to say delta dy was that. I'm going to say the height. The height equals. Okay, so just in English we could say that the change in position was negative, but the height of the cliff, like how high is that cliff? It's 15.09 meters. Really, I should go and change this to two significant figures because our data is in two significant figures. So when I round it, I'm going to say 15 meters. Now, so for question 21, now we're doing some horizontal work. It said if the car in problem 20 had an initial horizontal velocity of 26. So initial horizontal velocity, that's this one here, 26 meters per second. And in fact, the word initial here is a little misleading because it's the horizontal velocity doesn't change. There is nothing that's accelerating it in the horizontal direction. There's gravity that's accelerating things in the vertical, but this is actually going to be a constant. So we can actually say this is a constant, not just initial, but it's constant. So we can use this formula here. So it's pretty straightforward now. If we rearrange this formula to solve for delta D, it's going to be Vx times delta T. So I will get 26 multiplied by 5.5. And my calculator tells me that that is 143 meters. So there's my answer to that part. And again, I guess I should say two significant figures. So if I take 143 and I round it to two significant figures, I could write 140 meters, but then it's a little bit ambiguous whether or not that 0 is significant. So even better, it would be 1.4 times 10 to the 2 meters. Okay, you know what? Honestly, at this point, I'm happy with the 143. If you want to go to the extra step to turn it into scientific notation to show me that you know significant figures, that's good with me as well. What I'd like you to do at this point, I'll be stopping the video, and I'd like you to go to this textbook page, this handout, and so we've just done 20 and we've done 21. So what I'd like you to do is finish up to the end of 25. Okay, and there are answers for that. So each one of these ones is an example where we have something being launched horizontally, and so it'll be very similar to the question we just did. So try 22, 23, 24, and 25. Thank you.